welcome back to machine learning stuff. So as usual, I have some minor technical announcements and things to point out. I guess this will be common throughout the course. So here are some things I wanted to just mention before we continue the story. So what we were doing was talking about probability, and there was one question in Piazza, and various students asked me afterwards these kind of and it's like a very classic confusion that always comes up with everyone, including myself, all the time. And there's these three objects called the probability distribution, which we denote with this guy here, this double bar P thing. And then there's these two other things called PMFs and PDFs. And then there's always a confusion of are these things equal? What's the difference? When do I use one or the other? And this is the way you should think about it. At least this is my advice. So you should think of this probability distribution, this double bar P thing, as the thing you really care about. This is the thing that tells you the probability of some event happening. So it'll tell you what's the probability that my random variable, maybe the roll of a dice, is in the values 1, 3, or 5. So it'd be is one of the values in the event 1, 3, or 5. So the important thing is it takes inputs these events, okay? And then the way you actually end up calculating this probability distribution, because there's all these possible variations of events and it's complicated and you wouldn't want to list them out one by one and stuff, is you end up using PMFs and PDFs. So you should think of these PMFs and PDFs as just helper functions or tools or whatever that allow you to just calculate the distribution, P. So this is the thing you really care about, and then the PMFs and the PDFs are just these functions that help you calculate it. And another crucial difference is these things take as inputs outcomes, okay? And then the PMF and the PDF have different interpretations, one being mass, the other being density, and so on. But for the purposes of actually using them in most probability courses, you just need to know that they're tools to help you calculate the probability distribution. And that's the thing you actually get asked about. You ask what is the probability of something? That means what is the probability distribution evaluated for this event and stuff like this. Okay. A couple other things. So I'm just going to mention some more math notation that I didn't mention in the math class, but we're going to use so that we don't have to keep saying some longer sentences. And that's, we're just going to say this word countable set to mean that it's finite or countably infinite. So you know about the set's countably infinite, but also if it's finite or countably infinite, we're just going to use the word countable. Because as the word says, you can count all the, you can enumerate or count all the elements of a finite set or a countably infinite one. And then an uncountable infinite set is what you would expect. It's a set that has cardinality uncountable infinity. Okay. And this will be important for a couple little things that we'll see that I also made some changes to. And okay, the rest, we're just going to quickly review what happened last class, and I'm just going to point out these three things, what I mean by them. So we talked about these okay, the high level story, again, just to remind you, was that the thing we're going to care, why do we care about this probability stuff? It's because our data, this data set, is going to have these feature label pairs sampled randomly from some distribution. That's going to be the story. Then since these things are going to be sampled randomly, we're going to have functions like the learning function that's a function of a random variable D. And then we're going to see what the consequences of that and stuff is and why that's useful in this class. And the story was there's all this probability terminology. There's this field called measure theory, which is the more formal field, which we don't touch on at all in this course, but it causes for some things to be informal. And here's the things I wanted to point out from last class. So I mentioned there's these notions of a discrete outcome space and a continuous. Just forget about these terms. We're just going to call we're not going to actually use these terms at all. We're just going to have countable and uncountable, something is a countable set or an uncountable set. And the outcome space is countable or uncountable. And I'll show you what I mean in a second. But just kind of forget about this business. We're not actually going to use these words. And there's a reason, but we're not going to mention it. That was the one thing I wanted to mention from last class. The other thing is when we get to random variables, which were supposed to describe the fact that you do an experiment, you get an outcome, and that outcome is random. The random variable kind of represents this random outcome from your experiment. I said that, okay, we're going to think of random variables as always taking values that are real numbers, some as opposed to something like taking the value of like the word or like the letter H or the word heads or something like this. So we're also going to forget about this, and like the reason why is like formal, like it's a mixture of how people present it. Sometimes people say random variables are just numbers, and then they say these other things called random elements can be numbers or things like words, and then they distinguish between the two. And then there's other sources that choose. I'll answer the question online in a second, but there's other sources that just say random variables can be any random outcome. So it can be like the value heads, it could be like a picture, it could be anything you want. You can put anything you want in the set, and the random variable can represent that outcome. So the point is, yeah, like random variables can be, for instance, the letter H. It can be, it could be even a function, and it could be anything you want. And that's what we're going to do for this course, and it's just going to be easier. Anytime something is random, it's called a random variable, basically. Yeah. Okay. And then I'm just going to review one more thing, which was this idea of, this idea of a discrete random variable and a continuous random variable. So, and now it's going to use this, like, it's not going to use the word discrete outcome space anymore. It's going to use countable outcome space. And let me just rephrase what this all meant. So there's two types of random variables called discrete and continuous. A discrete random variable, right, is a random variable that takes values from the obvious cases if the outcome space is countable, which was either finite or countably infinite. So the space is, if you have a countable outcome space and your random variable takes values in that, then your random variable is definitely a discrete random variable. And then there's the other case, which is that your outcome space could be uncountably infinite, which is called an uncountable outcome space. But all of the probability is situated on what we would call like a countable event. And right, an event is just a set, so a countable event is just an event that is a countable set. So, for example, if we have the case of like throwing rolling a dice, and for rolling a dice, we have this outcome space that has like 6 possible values, right? 1, 2, 3, up to 6. Then the usual like probability distribution you talk about is, well, the probability of getting 1 up to 6 is, all of them are the same probability, and that's just 1 over 6. And then your outcome space would only contain these numbers 1 to 6. Now what the second point is claiming is that if your outcome space was the real numbers, right, but there was an event, such as the event of getting the numbers 1, 2, 3, 4, 5, 6, and that had a probability of 1, then this random variable, which takes values in this outcome space and has this probability distribution, is still called a discrete random variable. And once again, this satisfies the second property, which is that there's a countable event, which is this event, right? It's countable because it's just a finite set. And it has probability 1. And what that means is that everything else, like all the other outcomes, which is this event here, this is the event that contains all other outcomes. It's literally every other possible value has a probability of 0. And this should be like very intuitive. If you roll a dice, the chance you get anything other than 1, 2, 3, up to 6 is just 0. And this becomes important because it basically says what we had in this box here, which is saying that if you have a random variable kind of defined on some countable space, you can always extend it to a larger space and just set the probability everywhere to 0. Okay, it's kind of like intuitive and makes sense, but formally this is like the story. And why this was related at all to our setting is because we're usually going to talk about vectors. Vectors are elements of the real numbers, but usually they're good, like, okay, not usually, but there's some cases where these things are actually going to take values that are like in some finite space or discrete space, like maybe the number of rooms in a house. And so we're going to want to talk about it as if they're real numbers, but we're really going to talk about their distributions as if they're like discrete distributions and stuff. So that's going to be the story. It might not even be that important of a detail later on, but like it's useful to know if you notice these little details. Okay, I'm going to answer the question quickly from online, which was just asking what's the difference between outcomes and events again. So once again, you think of outcomes. So you have an experiment, right? And like for instance, rolling a dice, and the outcomes of that experiment are like the possible values you could get from doing that experiment, or like possible outcomes. So rolling a dice, the outcomes or the outcome space would be 1, 2, 3, 4, 5, or 6. Okay, those are all your possible outcomes. Like each value 1 or 2 is an outcome. And then an event is just any subset of this. And the way you think about it is like, for instance, a subset would be like maybe 1, 3, and 5. That's an event. Then you think about that event as representing kind of the event that you get either a 1 or a 3 or a 5. So yeah, like but formally, mathematically and stuff, events are subsets of the outcome space, while outcomes are elements of the outcome space. Okay. Yeah, and then in contrast, there was these continuous random variables. And if they're continuous, they have these uncountable outcome spaces, but with this extra property that the probability of any single outcome is 0. And that was written like this, which is the probability of getting any single value is 0. But still, the probability of getting any value in the whole outcome space is 1. And this is like quite counterintuitive and so on, but this is what you need to know. And I tried to kind of give some intuition through this idea of if you have like this continuous rod, and then the chances of you actually picking any individual point on a rod is like 0, but if you ask for some region, there's some chance you get that. Anyways, for the purposes of the class, you just need to know this property. Okay, and then there was this notion of how do you calculate probabilities? And the story for this was, if it's a discrete random variable, you use a PMF, like this PMF thing. And if it's a continuous random variable, you use a PDF. Okay, so this PMF thing is written as little p, and then the probability of some event, which is like this is the thing you care about, and the probability that the random variable is an element of that event is like the question you want to answer. Well, then there's just a definition through the PDF or PMF here, and this is what I mean by you should just think of it as like just some function that helps you calculate the probability distribution p. So yeah, you just literally like use this equation to calculate it. Okay. And then there's a similar story for the continuous random variables. In there, you use a PDF. We're going to use the same notation, but it'll be clear from the context. Like we say, like P is a PDF or a PMF. And here you think of P as representing like the density of the probability, and you use integrals because things are continuous. And once again, this is what I mean by it's just like a calculation. Like the probability distribution is just is defined as some calculation, which is an integral over the PDF. Okay, so the short story is what you should know by now is that random variables just represent like an outcome of an experiment. And if you want to calculate the probability of the random variable being some value, which means the random variable belongs to an event, you either use a PMF or a PDF depending on the type of random variable. And then you do some calculations and stuff. And then there's like common distributions and things like this. But yeah, we talked about them last time. I'm just going to skip over that. And okay, so now we start with kind of the new stuff for today, which is where we ended last time. And these are these multivariate random variables. And I'll quickly reintroduce what these are again. So multivariate random variables, you should just think of as these random variables that like can talk about multiple different types of events. So they're going to, okay, like we'll see in a second. But for instance, you might want to talk about getting heads and rolling like a 3 on a dice. Or you might want to talk about some wine containing 2.5 milligrams of one chemical or another chemical. You want to talk about different like the values, the outcomes of different experiments sometimes at the same time. Okay. Or another thing is like, what's the probability of a house having 4 rooms and 2 washrooms and being less than 10 minutes? So here you have like 3 different like outcomes you're trying to talk about. Okay. Formally, the way we represent this is just as a tuple of more than one random variable. So what that means is like if you, in the case of flipping 2 coins, you would say that now you have a random variable x. And what is it? It's a random variable that has like a pair of random variables. This first random variable would represent the flip of the first coin. The second one would represent the flip of the second coin. Okay. And then you could do the same things for other things. We talked about these examples as well. And so now we get into the place we really ended with, which is an example of how calculating probabilities over these like multivariate random variables looks like through an example. So we're going to go through the example to get some intuition. And then after that, we'll see like some formal math definitions of some multivariate random variable things. Okay. So let's get started. So in this example, you're interested in the following, which is like the cases of, this is like a hypothetical example. And the question is, if you have arthritis and if you're young or old, so like you have two random things going on here. The first is, are you young or old? Okay, so this is going to be your first outcome space. Young being represented as 0, old being represented as 1. This random variable x is going to represent that space. Then you have another random variable y, which is going to represent whether you have arthritis or you don't have arthritis. So no arthritis means 0, arthritis means 1. Okay, so here you think about this new random variable z as being the pair of these two random variables, each representing a different kind of experiment. Okay, and so in this case, you notice that both the random variables are discrete, and it turns out that the story ends up being like virtually the same as before, which is you think of this as just some random variable belonging to some outcome space. The outcome space here is this outcome space. Like, and more clearly, this outcome space, if you remember this thing, is like equal to, what is this Cartesian product equal to? It's the set of all possible pairs. So that would mean like you're young and you don't have arthritis, or you're young and you have arthritis, or you're old and you don't have arthritis, or you're old and you do have arthritis. So this kind of makes sense. It's just like your new space of possible outcomes is every possible pair. And once again, we see here how this Cartesian product becomes like a useful mathematical operation that allows us to define all the possible combinations of two sets. Okay, then the story basically becomes the same as what we would expect. You have a PMF, and that's just a map from outcome space, or I should say a function from outcome space, to some values between 0 and 1. And we're going to use this thing to help us compute probability distributions. Okay. So the story is that someone will usually give you a PMF. So I'm giving you the PMF here, okay? And then we're going to use that to compute distributions. So here's the PMF I'm giving you. I need to define what is the value it takes for every outcome. So that would mean what value does it take for 0, 0, 0, 1, and so on, these 4 things. So that's exactly what I'm doing in this block here. And just another note on notation is that you might notice you should take as input objects of this form, which are like tuples of 2 objects. And so you'd think you'd write it like this. And that's okay too, but most of the time people just avoid these brackets here and just write it like this to mean the same thing. Again, like these are equal, and we're always going to just remove the extra brackets just for like notational simplicity. Okay. So I've defined these 4 probabilities, or sorry, these PMF values. They're the following. This is like the first one, the second one, the third, and the fourth. It's much easier to understand these as a picture, so that's what we're going to do. There's 2 like visualizations that are usually helpful for these kind of things. One is you can do this like kind of table. So here we're writing the random variable x, which represents young or old, y, which represents arthritis or no arthritis. Then you can imagine here, this is just the value of the PMF at each of these combinations. So this, once again, is young and not having arthritis. What is the PMF value? It's 1/2. I just got that from this definition here. And then so on. So these are the things. Like I just plug them in. So it's much easier to kind of like see this in this table format. And oftentimes if it's discrete or something, this is the way it's much easier to view these things. And another way to view it is in terms of like the actual amount of like, let's say mass that this PMF takes up. So like 1/2 would take up exactly 1/2 of the total mass. So you could, so that's what this picture is representing. If you were to draw like this is like kind of like all the mass of something, then this case here, which is 0, 0, here, this PMF evaluates to 1/2. So it takes up like 1/2 of the area, okay? And then the corresponding other things, you can also draw their like area they take up, and you can see visually kind of how much each of these things take up, okay? The point of doing this is it's going to make like the calculations that we do in a second much more intuitive, but just like you can just kind of look at these pictures. And this is useful to get like some intuition and comfortable for the first times doing this. Obviously, when you start doing this in like midterms and when you actually work things out, you're probably not going to spend all the time drawing all these things, but this is like a helpful intuition to have to start with. Okay. So one other property to note that we were saying before is that this PMF should sum to 1. And what that means is if I just take the sum of this PMF thing over all the values of the outcome space Z, then it sums to 1. It turns out if I do that, I get 1. Unsurprisingly, I defined it that way, but this is what it means for it to be like a valid PMF. Okay. So now we're going to move on to computing the actual probability of something maybe of interest. And one thing we might ask is like, what is the probability of being young? Okay. And intuitively, that means what is the probability that a random variable x equals 0? And we don't care about the other one. Like it's regardless of what the arthritis, no arthritis, it doesn't matter. So like formally that event would be written as as this outcome here, which is young and no arthritis, or young and having arthritis. Okay, that's going to be our event. Usually this ends up being written something like this. You plug in, okay, so the thing you're interested in is the probability distribution of this event. And instead of writing something like this, which is totally fine, and then like that's the formal way to do it, it ends up being written as like the kind of the cases for the two random variables, which is that if you're interested in young, which means x equals 0, and you don't care about the other things, then you have y belongs to every other value. Okay. And the way you compute this is exactly through the definition that we had of like how a distribution equals a PMF. It's exactly this thing. And plugging things in, what you end up getting is the following. Like you expand the sums, but the main thing to notice is you get this thing. You get the PMF of 0, 0 plus the PMF of 0, 1. Okay. What does that mean visually? That means you go to this picture here, and you take this area, which is the area or the mass of being young and not having arthritis, and then you add it with the area of being young and having arthritis. This gives you the total probability of being young, right? Like you just do the case where you're young and every other possible combination of all the other things, which is only 2 in this case. So what we would get is that the probability of being young in this case is 51 over 100, or 51%. So hopefully something like this makes sense. It's just like intuitively makes sense, hopefully, and then like the math is there. Okay. Yeah, there's a question over there. Mm-hmm.
So would that ever be different for a different PMF? Because isn't the total of the values always 1? So, what does that denote in this problem?
Yeah, so let me so the question is kind of like the so the question was, the PMF here was written like this. Is this like always going to be the case? Does it always map to 0 and 1? And the story is yes. And we can just go back to the definition here to just like see what happens. And we say like a PMF is a map always from your outcome space to 0, 1. And it has this property that the sum of the PMFs, like at all the values, all the outcomes, ends up being 1. So it clearly can't be a number larger than 1 because it sums to 1. Sometimes, like, yeah. So this is always the case. This is in contrast to the PDF, which can map to infinity because it represents density. You can be like really, really dense in a very, very small region. And then if you want to get the mass for that region, you would just multiply the density, which is a lot, by a really small like region or area, and you get the corresponding mass. So that's okay. So that's why this thing can be like 0 to infinity, but when you integrate it, you end up with 1. And once again, you can have like things like this. So you could be very small, like distance here, but the actual value is very large. And that's also okay. But that's an important thing to note. Okay. So this is like our first thing that we saw of joint or multivariate random variables, and we call their distributions these joint distributions. Like they're joint over all the random variables. Okay. Then it turns out there's like a few things that we would want to like talk about with these joint things, and they have special names. In particular, the first thing we want to talk about is maybe like the distribution over just one random variable from that whole multivariable thing, or just like a subset of them. That turns out to be called a marginal distribution. And that's exactly what we actually did above. Here we talked about only x equaling 0. We didn't really care about the other random variable. So in general, okay, let's yeah. There's some notation for this, and we continue with the previous example because we've already almost worked all of it out. And the notation is the following. You take the usual distribution notation, and in the subscript, you put the random variables with which you're taking the marginal distribution over. So this means we just care about the distribution over x, forgetting about kind of every other random variable. In this case, that's just the other random variable y. Okay, and so unsurprisingly, this talks about events which are subsets of only x, the outcome space x. It doesn't talk about events that are from the other space. That also makes sense. And it has, everything becomes almost the same story as before, which is now, for this distribution, it has a PMF. That PMF, again, is denoted with the subscript x. And that just talks about the probability mass or whatever for a function that takes outcomes only from x and maps to 0, 1. Okay, and then the story is, okay, and it's defined through this special definition, which is you take the the joint kind of PMF, and you sum up all the other random variables, which is represented by this. So you fix this x value, and you take the sum over all the others. And we'll see the general formula in a second. But this is exactly what we saw here, right? Which is you fixed x to be 0 in this case, and you took the sum over all the other values. Here, there's only 2 other values. In general, you could have a much bigger sum. Okay. And so once again, what we saw in our example, it's exactly the same story, is that you would actually write something like the marginal distribution over x, which is this, and then you would just write as input this random variable, x, and you would say what's the probability that x equals 0, which you should always remember. This thing here is actually means x is an element of the event that contains just the value 0, right? The distribution always talks about events. Here, the event is just one, the random variable only equaling one value. So there's this shorthand notation. Okay. Moving on, yeah, there's this PMF for it, and then you just do the calculation as we said above, and we get this value that we already got in the previous example. This should make sense. It's the probability only for x. Okay, the probability that you're young, right? X equals 0 means that you're young. Similarly, this thing also defines the other values of this random variable x. In particular, this 1 here, this means that you're old. And so you can ask, what is the probability that I'm old? You can just visually do this, or you can do the calculation. But the story is, unsurprisingly, it's 49 over 100, which also makes sense. It better be 1 minus this thing. So it's 49 over 100. Visually, what that means is you take this green region here and then add it to this green region. These are the 2 cases where you are old, right? This one representing you're old. So you could always do this kind of intuitive visual analysis too for these discrete random variables with not too many outcomes. So hopefully visually this would make sense. So right, there's 4 possible outcomes. These are the cases where you're young. There's 2 of them. These are the cases where you're old. There's 2 of them. You add up their total, their probabilities to get the corresponding marginal one. And so in general, the story becomes for these marginal distributions is that if you want the distribution over just one random variable, then what you do is you kind of fix that random variable and then sum over all the others. And what that means is in general, you might have a random variable that has d kind of dimensions or components to it instead of just 2. And then the corresponding PMF, which is this thing, for random variable xi is you fix xi, and then, so you have xi here, and it's going to be fixed, and then you sum over the PMF of everything else. Yeah. So you basically sum over all the other possible values. Just like above here, we fixed one thing, which is this is 0, and we summed over all of y. This way we just have more and more variables, but the story stays the same. And then the story is the same for these continuous random variables. We haven't done an example for it, but everything is essentially the same story, except now you use PDFs, and now you use integrals, these integrals, instead of using the sum. And once again, you hold this xi constant, and you integrate over all the other variables. Yeah, you can, this will be in the notes, and I shared the notes online as well, so you can see this more formal story, but okay. So these were these marginal distributions. where when you have multiple variables, right? So marginals only make sense when you have a multivariate random variables. Why? It's because a marginal is exactly saying I only care about one random variable in that whole multivariate random variable, or maybe I care about some subset of it. But for this course, we're always just going to do one. So, okay. So like intuitively, that should make sense. Another thing that might happen when you have like multiple things, multiple variables, is you might want to ask what's the probability of like one random variable or like one outcome given another outcome. This is called like the conditional distribution. It's like what's the probability of something conditioned on something else happening. In the arthritis example, this should like intuitively also make sense. Like what's the probability that I have arthritis given I am young? This is something you'd want to be able to like write down, and formally we can do this with these conditional distributions. So yeah, this is an example, probability that I have arthritis given that I'm young. And so in this, for this one, I'm going to give the formula first, and then we'll use it in the example in a second. Okay. So once again, there's these two cases. There's the discrete case and there's the continuous case. And in particular, that means the random variable y is discrete or it's continuous. And remember here, so this is still following with like the kind of like the previous example. We could think of y as the probability of arthritis or not. Okay. So then you would write the PMF for this thing. Okay, so the story is going to be the same. There's going to be a distribution. It's going to be called the conditional distribution. It's going to talk about the probability of y conditioned on x. This is how it's written with this bar. And it's going to be, as before, defined through a PMF. Okay, this is the PMF is going to allow us to compute this thing. What's the PMF? It's the following definition. And so here's the definition. We're going to use it in a second, and I'll give like just a very brief kind of intuition of why this might be the definition, right? So we want, once again, going back to the example, we want to know what's the probability of like, let's say, having arthritis given I'm young. Intuitively, how would I like do this? Like one way to think about probabilities is imagine we have like 100 people, right? So how would I like get an idea of what's the probability of me having arthritis if I'm young? Well, I would look in this population of 100 people, how many of them are young, right? I would just look at the people that are young because I care about out of the people that are young, who has arthritis? So I would first only look at the people that are young, and then out of those people, I would count how many have arthritis. And then I'd probably take that ratio, and that would make sense to be like that's more or less the probability that someone has arthritis given they're young. And that's exactly what this formula says. So this is, in the denominator, we have the probability that you're young. And you can always think of these like probabilities, which are like fractions or like percentages, as just like a count of the number of people. And so for like intuitive purposes, but anyways, this thing represents the probability that you're young, and the top would represent the probability that you're young and you have arthritis. And so the intuition should be like this kind of, is exactly the ratio of number of people that have arthritis and are young divided by number of people that are young. Okay, so that's the intuition I want you to kind of have for this. But when you're doing calculations and stuff, you're just going to use this formula, which means you have this thing, like, okay, I'm going to give you this thing, which is called the joint PDF or PMF or PDF. I'm going to give it to you, just like in the previous examples, I gave it to you. You're going to maybe calculate this, or maybe it'll be given to you as well. It's the marginal PDF or PMF here. And then what do? You just like use this formula. Okay, we're going to see an example in 1 second. Story is almost the same for the PDF thing, and I'm just going to quickly repeat it, which is that, once again, what do we care? Like, we have a continuous random variable, but the thing, what do we care about? We care about its distribution. This thing is exactly the same as above. This is the distribution of y given x, which just means the distribution of like, what is the probability that y is an element of some event given x equals something. Okay. And once again, as with all the distributions, they're defined through either a PMF or a PDF. Here it's defined through a PDF. Then you just need the definition of the PDF and you can get this thing. What's the PDF? The PDF is exactly as what you saw for the PMF case. Actually, it's exactly the same fraction, but now this thing is a PDF instead of a PMF. And the only thing that changed is when you compute the probability distribution, you use an integral, as before. And once again, this is because the random variable is continuous, meaning it takes values on like an interval. Here I haven't written an interval, but yeah, anyways. it takes values on an interval. So you can imagine this is maybe like an element of 0 to 1. That's an example. Okay, so now let's go over an example, or maybe I'll answer this question first. So the question is, why does the PDF map to 0 to infinity and not 0 to 1? Okay, so that was the question. I think we already had the question earlier, so it's good to see that there's like, clearly there's some confusion, and this is really common in probability courses. Like, this PDF thing is probably one of the weirdest things for people, and it's not, it shouldn't be surprising. Like, first of all, for continuous random variables, the probability of something equaling an exact value is 0. Then you have this PDF that can actually be almost up to infinity. Like, what's going on? And yeah, once again, I'm going to give a slightly different maybe story, but this kind of the same intuition, which if we think about like this rod, for instance, here, you should think of the PDF as giving like the density, which means how much mass is there in a given area. And you can imagine that density could be much larger than 1. You could have like much more than, let's say, like 1 kilogram per centimeter or something, or per meter. You could have much more than that mass, as long as that region isn't too much, because you want the whole mass to sum up to 1. So what you could have is, you could have, like, for instance, this plot could be something like this. And the thing you care about is the mass, so this would be the area under this thing is 1. But this plot here, this green thing, is the PDF. And so the density, which is like the probability density function, the density can be much larger than 1 in places. But the important thing is that it's not for too long. So it's not for too much area or too much like of this distance. Because the thing you're going to actually care about, like the probability, is going to be the area under this PDF, right? This is the way we think about it. We're using integrals of a PDF, which means like an integral of a PDF means the area under the PDF gives us the probability. So yeah, that's the story of why. Maybe that clarifies it, but yeah. So back we go. And there's another question. Someone asked, the mass adds up to 1 for a density. And the answer is yes, the mass, or like when you take the integral over the whole PDF, over the whole space, it always gives you 1, because that's the total mass, and that always has to be 1. And you think of total mass as like the total probability. That always has to be 1. And there was one more question, which is this random variable y conditioned on x is y divides x, right? I'm not sure. No, so like, okay, I think the question is like, does this mean y divided by x? The answer is no. This notation is just shorthand for, okay, I should have mentioned this probably here. So you should think of this thing here, like this, for instance, this PMF, this conditional PMF, as a function of only y. Okay. It tells you, I want to know, it gives me a probability distribution, or sorry, well, this PMF is not going to give us the probability distribution, but we're going to get through it. But you should think of it as just talking about the random variable y, the values that takes. Because, like, what is this distribution? This distribution is saying something like, what is the probability that I have arthritis or don't, conditioned on x equaling a very specific thing. If I change x, I get a totally different distribution. So for every value of x, I will get a totally different distribution for y. So that means that the PMF changes for every x. It can change for every little x value. And instead of writing it in this like complicated denominator way, showing that like for different values of x, this thing is actually different, which makes sense, right? Like if I'm old, there should be a different probability distribution over me having arthritis or not, versus if I'm young, the probability that I have arthritis or not should also be a different probability. So you wanted to, these things should be different, and they usually are. And the way this is written is like this. This is like the shorthand notation that's used. Is instead of writing this thing in the denominator and clearly indicating this is only a function of y, which is like this thing is clear, it makes it more clear. People write this. And so here you should think that y is the input. It's only a function of y. But you put x here to mean like it's specifically this conditional PMF for this value of x. If I change x, this thing actually, the function itself changes. And this can be really weird and confusing. But intuitively, it should make sense. Like if I change the thing I'm conditioning on, I should get a different distribution over y. And so yeah, there's all sorts of this notation in probability, which gets really annoying because then you're like, wait, is this thing a function of x? Is it a function of y? Like, is it a function of both? And I try to always start with like the underlying notation, which usually isn't even mentioned in probability courses. They just give you all this, and it's like, and this is all just shorthand notation to like really mean something like this. And yeah, so I'd say like one thing just to step back is I always recommend just like thinking about the underlying story of what's happening, such as like what are things actually functions from. And this is why I'm really trying to emphasize this like notation of writing this is a function of this to this, because it makes it very clear that this thing is taking as inputs y's. It's not taking as input y cross x. It's just taking input y values and so on. And yeah. And this makes things very precise. Hopefully it doesn't confuse you more than it helps, but yeah. Okay. So before going into the example and one more thing, we can quickly step back, right? What we did so far was talked about these multivariate random variables. It's just a variable that is represented as like a tuple of many other random variables. And there's three kind of distributions you're going to want to talk about here. There's the joint distribution, which is the distribution over all of them at the same time. Then there's the distribution called a marginal one, which is just a distribution over one variable in that tuple. It means like fix that one random variable, don't care about any of the others. That's called the marginal. And then there's a third one, which is like the distribution of, or when I say distribution or probability, these are all kind of the same word. It's the probability of some variable conditioned on the other. And that's called the conditional distribution. So there's these three distributions. They're going to come up a lot. They actually are all related through this exact property here. And now I'm going to mention a couple more properties, which are just literally rearranging this equation. And these you may have heard before. So there's two more called the product rule and Bayes' rule. Product rule is exactly rearranging the above equation. You take this thing, and now you say this thing is equal to the thing on the left multiplied by the denominator. That's exactly what you have here. And sometimes this like rearrangement is useful. It has a special name called the product rule, like it's just math manipulation. But like intuitively, it also has like a pleasant kind of interpretation. So you would read this as like the probability that I have, like, okay, this is through the PMF, but you can do the same thing. Like you can always kind of think of this at least for the PMF case, you can think of the PMF as actually representing the probabilities at the specific points. So I'm going to read this as the probability that I'm young, let's say, and have arthritis. This would mean like I'd plug in 0 here for young and arthritis as being 1 here. What is that probability? Well, that's the probability that, and I'm going to do this version here. It's the probability that I'm young multiplied by the probability that I have arthritis given I'm young. So it kind of makes sense. Like the probability I'm young and have arthritis is intuitively like the probability that I'm young multiplied by the probability that I have arthritis given I'm young, which I've already accounted for. But if the intuition isn't your favorite, then there's the math expression that formally says the story. Yeah. And then there's Bayes' rule, which is exactly this thing with the numerator replaced with either of these properties. So yeah, that's all that happened there. And this thing is called Bayes' rule. And the only, like, why would this be useful? It's useful because sometimes it so happens that you have access to this thing and to this guy, and you don't have access to the joint thing, the joint distribution. Sometimes this happens in real life, like you know these two distributions, or these two PMFs, let's say, but you don't know the joint one. So then you can do the calculation as well. Okay. So now let's go over an example of kind of using some of these things. Oh, and I guess before the example, I tell you more notation things that you're probably going to be annoyed with. It turns out that a lot of the time, people will just suppress the subscripts of things. And then you once again have to just guess what things mean, but usually it makes sense from the context. So what that means is like we used P to mean the joint PMF or PDF. You could be more explicit and write x comma y, or in general, like if you had more variables, you might write something like x1, x2, whatever up to like xd. But you can imagine this becomes very like cumbersome putting all this in the subscript. So oftentimes it's just suppressed, and it's just obvious that this is the joint one because it takes in 2 inputs. Same story for the marginal and the conditional versions. In the marginal case, you will suppress this x, meaning that I'm just care about the distribution over x. And you would just write something like this. And here you should just understand this is the marginal because it takes as input one thing. And here is maybe the value of using this like weird notation instead of just writing y for this conditional version, is because instead of writing like this kind of thing, you can now clearly see that this is the conditional by writing something like this without the subscript. And yeah, and you should remember this thing is only a function of y. And this like bar x, and maybe just one more thing to remind you is like, you might remember that we use some notation like this, which is like x may be element of, and we use the bar here as well, which meant like condition or like condition on or like subject to something, maybe x being greater than 2. So this in math is a symbol that's often used to mean like such that, subject to, conditioned on, like this kind of thing. And that's how you should read it here. So this notation is kind of like, at least they're commonly used across math in this way. So yeah. So we're going to remove subscripts in places. You'll see this all your life in probability. You'll see it occasionally in the course. We'll try to make it clear by indicating what's what, but keep this all in mind. Okay, let us go over an example of this now. Similar arthritis example. And I don't know if I said it, but the actual probabilities are not like real probabilities, not real data. So don't be using this to make your decisions or something. Okay, so here's a question we might ask. The question is like, what, and okay, maybe just like to give some motivation, what are we doing here? Is like, we're doing all this probability stuff. After we do this example, I think we're finally going to be able to talk about what this looks like with the actual like data set and our learner and stuff. And I have the notes for that coming up after this. So like we're getting there. After this thing, we almost have all the tools to kind of like see how this is related at all to machine learning. Okay, so let's just get through this example. So here we might ask, what is the probability that I have arthritis given I'm young? And I've said this like a couple times, foreshadowing this example. So here it is. You write this distribution. The probability that I have arthritis, meaning y equals 1, given I'm young, which means x equals 0. What do we do? Like, what we're going to do is just use the formula, which means the distribution is equal to like a sum of the PMFs. Which PMFs? Well, the PMFs that represent the conditional, like the conditional, so there's a conditional PMF. And yeah, we use that conditional PMF, and what do we plug in? We plug in y equals 1, x equals 0. That's fixed here. So you get something like this. But like, what is this conditional PMF? We never calculated, no one's given it to us. So what do? We use the formula. And just to remind you, the formula is like, is this kind of formula here. Okay, so let's use the formula. So at the top, we have the joint distribution. At the bottom, we have the marginal, like, okay, I'm being imprecise. At the top, we have the joint PMF. At the bottom, we have the marginal PMF. We've already computed these things. This was given to us. This we computed earlier. In the case where we asked, like, what is the probability of being young? This was fixing this. Beautiful. So now what we can do is we can just plug those in. So we have this value to begin with, like that was just given. This thing we've computed as the sum of holding like x constant as 0, like the thing we care about, being young, and then adding all the versions of y. And so what do we get? We get, like, when we plug it in, you get some math, you get 1/51. Okay, that's a number, great. That means the probability that you have arthritis, given you're young in this example, is 1/51. Let's go over the intuition, like visually, about what this formula kind of means, and hopefully this will be good intuition for the calculations in the future. So we started with a picture like this, right? And the orange region was the probability of being young. It's all the cases where you're young. The green region is all the parts where you're old. Here 1 means old, here 0 means young. Okay. What do we care about? We care about the probability of having arthritis given you're young. So you should only care about the region that's the young part, which means we should only care about this like orange region. So that's all we're going to care about. So then let's just talk about the orange region. So that's this. Okay, so that's what it means to condition on being young. Now that we've conditioned on being young, you can imagine the picture would be different if we condition on being old. You take just the green region, and then you talk about that. So, but in this case, we're conditioning on being young. And now we talk about what's the probability of having arthritis or not having arthritis given we're young. What does that story look like? Well, those are the two cases we have. Like this one right here is y equals 0, meaning you don't have arthritis. This is y equals 1, meaning you do have arthritis. Intuitively, the probability that you have arthritis, given your, like in this case, it would just be this over this area. And that's exactly what we have here. This thing's 1 over 100. And this thing's 51 over, okay. It's 1 over 1, okay, like forget about this 100 part, because this is like in the original place. This is technically, it takes up like 1 square here, and here, this 51 is the total area of this. Yeah, sorry. So out of the 51, you can think of this like out of the 51 people that are both young, or that are all young, there's 51 people that are young. One of them has arthritis, and then 50 of them here do not have arthritis. So what's the probability of being young and having arthritis? Well, it's exactly that ratio, and you should think of it as like 1 over 51. And these hundreds cancel out, of course. Okay. The story is that like you can calculate these conditional things in either direction as you want. You could actually ask questions such as like, what's the probability of being young given I have arthritis? This is the other story. And to do this, you can like visually do it. You can mathematically do it. Like visually, what would that mean? Now I'm conditioning on having arthritis. So I would look at all the cases that have arthritis. That would be like 1 and 1 and 1 here. So that would be this whole region. So I would just look at this thing. And then what would I do? I would take the fraction of this over the whole area. Or I do the math. Turns out when I do that, I get 1 over 40. I'll just leave that there. And once again, intuitively, that makes sense. Like if I look here, I have 39 people that you should think of as being old and have arthritis, and 1 person, right, this is 1, that's young and has arthritis. So what's the probability of having, what was the thing? Of being young given you have arthritis? Well, it's 1 over the total area, which is these two together. Okay. Yeah, cool. All right, so actually there's one more property that's important called this independence property. And so once again, this also becomes kind of an intuitive story, which is that we say that two things, like two random variables, are independent of each other if one random variable doesn't affect the probability of another one. There's 2 ways that this is kind of represented mathematically. One is that this joint PMF is equal to the multiplication of their corresponding marginal PMFs. And here I've used the like shorthand and with not putting the subscript, but really you should think of this as for X and this for Y, right? These are the marginal PMFs. So this is maybe a little bit more cryptic than the other way to understand it. And I'll answer the question in a second, which is the other way to understand it is like, you remember that there's this product rule. This is not right. Let's fix that. There is this product rule. That's just the equation, right? But above, I just said that this thing, like, I just said that this thing has to equal this kind of thing. So that means each one of these terms has to equal like this. What that implies is very intuitive. What that implies is that these conditional distributions actually don't depend on what you're conditioning on at all. How do we see that? It's like you would write the conditional PMF of X given Y. Well, it just equals to the marginal PMF of X, meaning that it doesn't matter what Y you put in. Every Y you put in, you get the exact same function. Okay? That should make sense. Like independence, like this kind of like maybe the most intuitive one, which is that independence means that no matter what you condition on, being young, being old, being, I don't know, in this country and stuff, it doesn't do anything to the thing you care about, which is maybe like the flip of a coin, let's say. Like probably the flip of your coin doesn't depend on if someone's young, on whatever, like it's going to be the same thing. So that's what this is. Doesn't matter what you condition on, it's going to be the same story. Okay. Yeah, and more generally, this is like, you write it as this, is like, if you have a joint thing over many random variables, then it's just the product of all of them. That's like the general story, but once again, most of the time I'll work with just like 2 things, I'd say, and this is this thing to remember. Okay, let's just leave it there. And just as 2 quick examples, if you work things out, you'll see that for the arthritis case, unsurprisingly, and maybe to the pleasure of our intuition, is that the random variables are not independent, meaning that like the chances of you having arthritis, or the probability of you having arthritis given you're young, is not independent of if you're young or old. It actually depends on it. And the way you would work that out is you would just calculate this probability, calculate the 2 products, and find that they're not equal. And they have to be equal if they are independent. While for something like flipping a coin, you might represent x1 and x2 as the flip of the coin. When you write things out, you end up that they are independent, meaning like that this product equals to the joint distribution. And like visually, you look at this table, they're all 1/4. You can always sum up each thing and get 1/2 and so on. And yeah, if you just look at the example, it should be pretty intuitive. Yeah. Okay, I shouldn't speak too soon because the thing you're going to see in a second is that you're going to have n random variables being independent in the data set. So I'll explain that in a second. You're not going to do like much math with it actually, but you need to know the intuition that like, yeah, you might. Okay, we'll see. It's like it's not going to be expected of you to do much math, especially on midterms and stuff with that many random variables. But you might be asked like, if you know like you have n independent random variables, then what does that mean, for instance, for its joint PMF? Well, that means that you can just write it as the product of all of it, something like this. You would never need to compute all this stuff. Okay. So you would have like a more complicated story for Bayes' rule because you'd have now, you condition on many random variables, and then you'd have like the marginal over either one or maybe some of them and stuff. But yeah, we're not gonna do the calculations. But did I mention it here? Yeah, like in general, like things like the product rule, you can write for more random variables, and you have like conditioning on everything up to, this should be d minus 1. So maybe I'll put this. You condition on everything up to d, and then you condition everything so on and whatever. But yeah, there's a formula. You're really not going to need to know. You just need to know the case for true, and the intuitions kind of extend onwards. Like you're not going to have to work out the math. Okay. So shall we move on to, okay. So there's one thing I wanted to point out, and for the sake of time, what I decided is that there's a couple examples coming up that I think are quite useful for having some intuition in the course, and just, yeah, like especially in later parts of the course. And I have like 2, I think, nice examples to work this through, but I'll do them so they're in the notes. They're going to be in the course notes as well. They're like in these notes and the course notes. I'll write them up. But I'll go through them in the tutorial because they're just like working through some math steps and stuff like that, which will also be recorded this Thursday, and then you can watch it if you want, read this if you want. I'm just going to explain the high level like story of what the example is about, and then you can see the math steps to work it out after. But this is like kind of quite relatable. Okay. So here's one of the examples, which is the question is, so far we've seen these multivariate random variables or joint probabilities and stuff over the case when x and y is both discrete or both continuous, or you have more of them which are, so all of them are discrete, all of them are continuous. But the question might arise, which is what happens when y is discrete and x is continuous? Or the other way around, like what's the story here? Like what is this thing? Is this thing a PMF or a PDF? Well, it turns out it's neither. And yeah, like it's called like a mixed thing. I don't even know, like it's called like a mixed PDF or PMF. But the story is like, what do you do then? How are you going to calculate your probabilities? And the answer is you use the product rule. What does that mean? So whatever this object is, we're not going to give it a name. It's like some mixed thing. It's equal to something like this, it turns out. Turns out this still holds. Okay. And then, remember, this thing is just a PMF over a single variable. This thing is also just a PMF over a single variable. Remember, this thing is not an input. It's just like notation to make things more intuitive. So now you have two PMFs over single variables. Now, it doesn't matter if they're continuous or discrete. You can just assign you can use their corresponding PDFs or PMFs. So for instance, you might say that, well, you might be told that, like, for instance, this thing is a discrete random variable, so you use a PMF. Okay? And then you might be told that this thing right here, this x, is a continuous random variable, so you use its PDF. So this turns out to be useful. Let me just give like the setup of the example. Like, here's the setup. Imagine x kind of represents the amount of a chemical in your wine. And imagine y now represents the outcome, which is it this Barella wine or not? Right? You now have a mix, you have two random variables. One's continuous, which is like the amount of chemical. The other one is just this binary thing that's like either Barella wine or not. It's a discrete set. It's a discrete random variable. And then you might want to calculate, like, what is the probability that I have a Barella wine given some amount of a chemical? And so to do this, you're going to end up needing to use like this kind of property here. And yeah, and the story is like, you're going to try to write something like this. You're going to plug in P here, and then you're going to plug like that product rule in, and then you do the calculation and so on. So we'll go over this in more detail in the tutorial, but the point is this comes up, and you're going to see this in this course. And it's going to be important to understand that when we ask for like the probability of something like this, one is like discrete, one is continuous. You're going to have something that has an integral, something that has a sum, and you're going to have to break up this thing. So yeah, this is, I'm warning you, like, I would really recommend trying to like get comfortable with what happened here. Okay. Finally, we get to the actual point of the machine learning part and how this all was at all related. Okay, so let's talk about that. So this title here is representing these random features, labels, and data sets, right? So I said these things are all kind of like, where did we get the data set? Where do we get the features? We think of them as randomly we think of like we randomly collected them in some way. This is how we would write it. So now I'm going to use, instead of this like calligraphic, before you might have noticed I was using like a calligraphic D. Now I'm using just the capital letter D to denote the data set is random. What is the data set? The data set you can think of as n random variables. We've seen these things, right? Like we just saw multivariate random variable, there's n of them. One like very simple case, imagine n coin flips. This is not the coin flip case, but you have n random variables. You can think of them for like simplicity's sake as just n coin flips. We've seen that this thing is going to have some distribution, we can do these like conditioning and things like that and so on. Okay. It turns out that it's okay if these things themselves are multivariate random variables as well. So each z can itself be a multivariate random variable, such as zi equal to this multivariate random variable. What's this random variable? Well, this one has the intuitive interpretation of being a feature label pair. So now we read D as the random variable containing n feature label pairs, each of which is itself random. Okay. Finally, inside each feature label pair, you're going to have like a feature and a corresponding label, and the feature might itself be this like complicated thing which has d dimensions and has like, which would be corresponding to the d features. And you would call this thing like a feature vector. Okay. That's going to be like the kind of the outcome. So what's the outcome space? The outcome space is this like complicated Cartesian product of n of these z's. Each of the z's themselves is this feature label pair outcome space. And then the feature itself is this like d-dimensional outcome space. So there's like a lot of this nesting going on. But the thing to note is if you just like represent each feature label pair as some random variable z, the story should become very nice here, which is that once again you have n feature label pairs, each of which is its own random variable. Okay, great. This is kind of the outcome space and the random variables we're working with. Now let's talk about the fact that each of these random variables is associated with a distribution. And there's really going to be like two distributions that there's going to be more, but these are the two main ones. So first of all, this thing is a random variable. Each random variable has a distribution. So there's obviously some distribution from which the data is coming from. We're usually not going to like talk about this complicated distribution. We're not going to like actually define what it is and things like this, but what we need to understand is that it is a distribution, okay? And it's a distribution over this random variable that has n random variables in it. Okay. Each one of the random variables in it has its own marginal distribution. So that means P of Zi, that's the marginal distribution of each Zi. The way to think about this is that each feature label pair, and this would maybe mean something like the number of homes and its price, that joint random variable, multivariate random variable, has its own distribution. That should be like a little bit more intuitive, like the probability that I get some number of rooms and a corresponding price has some probability, while another number of rooms and price might have a smaller probability, and so on. That has some distribution, and that's like the usual distribution we're going to actually usually care about. It's going to be that distribution from which we actually gather features and their corresponding labels. Okay. So here is the common assumptions that end up happening in this like supervised learning setting, which is that, first of all, we assume that these random variables, which is each feature label pair, is independent. And we're going to see what that implies in a second, but you might remember that means like that this joint probability like distribution is just the sum, or sorry, not the sum, the product of all the individual ones. That's going to be a really nice property. And the other assumption is that usually you think that each of these random variables comes from the same distribution. Okay, so that means P of Z1 up to P of Zn, all of these feature label pairs came from the same thing, meaning that like you're randomly collecting n like house price pairs. Or if you think about coins, that would mean like if you had n coin flips, they all come from the same distribution, which is the distribution of like just flipping a coin. It's all a fair coin or something. So that should also be kind of intuitive. So like, I mean, it's not always true in the real world, obviously, when you gather data, but like this is the simplifying assumption that's made so that we can do some like nice math and get things that actually work mathematically afterwards. What is that really? Okay, first of all, you might hear this terminology, which is really useful to know, which is that you might write something like these xi, yi feature label pairs are independent and identically distributed, and often written as IID in like a probability or stats course. This is exactly the way you would think of like if you have n coin flips, each one of them is independent of the other coin flip and identically distributed. Same way you think about gathering n house price pairs. Okay. Finally, what this really implies is that this probability distribution over the whole data set D, right, takes in all these different, this should be n. Yeah, why did I have that? Okay, let me fix that. These should all be n, right? You have n feature label pairs. D is just the dimension of each feature. Okay, great. Good thing I caught that. And this is all n. Okay, great. So this is the distribution, P of D is the distribution over my n feature label pairs, my like n house price examples. And since we know each one of these Zn, it's like Zi random variables, is IID, they're identically, well, importantly, they're independent. What that implies is that when first of all, I can write it out as this product. These are all multiplied together. And since they're identically distributed, I can just replace all of these distributions with the same distribution, which I'm going to call P of Z. These are the same distribution they all come from. Once again, I think it's useful to remember kind of like the coin flipping example. In a coin flipping thing, you would think this is n coin flips. E's are just like, what did the coin flip become? You might ask, like, is the coin flip heads here? Is this coin flip tails? Then you would say that since the coin flips are all independent of each other, the probability of getting any sequence, which would be like heads, tails, heads, heads, whatever, tails, is just the probability of each one, which would be 1/2 times 1/2 times 1/2 times 1/2, n times. And then finally, like instead of writing like each coin having its own distribution it's coming from, you actually like usually it's assumed that the coins are all coming from the same kind of distribution, the fair coin flipping distribution. So that's the useful way to kind of like think about this whole story. Okay, let me just say one more thing before I take this question, because I really wanted to finish this. Yeah, so okay. So we think of, and often it'll be written in this shorthand, and this is how I wrote it at the very beginning, which is that you say D is your random variable. Explicitly, it looks of this form, n feature label pairs. This random variable belongs to this outcome space. The outcome space we've already seen. This is why we built up this Cartesian product notation and everything. It belongs to this outcome space. This shouldn't be too surprising. Oh, this is not a comma. Cartesian product, okay. Belongs to that outcome space. And finally, the important thing is that each one of these XY pairs comes from the same distribution, and they're all independent of each other. And this is like a compact way you can write it. And to really drive the point home, I wrote it in English to clarify one more time, which is that you can think of this as this random variable D containing n independent samples of these feature label pairs, all coming from the same distribution. Okay. I'll answer, oh, sorry, yeah.
The independence assumption does not mean that X is independent from Y.
No, that's very important, yeah. So X is, that would be really, like, what are you doing then in machine learning? Like, if the price of a house is independent of its feature, like its description, like the number of rooms, the age, then what is there to learn? Like, if Y doesn't depend on X, then there's nothing to learn about Y from knowing X. It's definitely not like assumed that Y, like it's actually assumed that Y is very dependent on X. Sometimes it's like a perfect function of X in the like simplest case, which is like the price is exactly, let's say, like the number of rooms times 200,000 or something like this. I don't know. Like that would be a perfect, let's say this word correlation or dependence. Like so Y almost all, like when we work with things, we always assume that Y actually does depend on X and quite heavily depends on X. That's exactly the thing we're trying to learn, is like kind of that dependence. But each of those pairs, like the house and then its price or whatever pairs, feature label pairs, those are independent of each other. So like one house, the info about one house and its price is independent of another. So like this price of this house didn't influence the price of another house, and so on. Obviously, that's not like really true in the real world, but it's assumed, and it's, I guess, sort of close enough in some cases. Maybe not in the house thing, but in some other example, it's very clear that that would be true. Yeah. Okay, sorry.
Yeah, right there. So, like, the probability distribution of like the data set. So, I was wondering about the events, like event 1 to event n, right?
Mhm.
That,
Yeah, right. So the events here, right, they would be subsets of the outcome space of Z, right? What's the outcome space of Z? Well, let's go up here. This is the outcome space of Z. It's just the Cartesian product of features, like the set of all features, with the set of all labels. So what is this set? This set looks like this like set of all tuples, all pairs of every possible feature and price, or feature and label pair. Okay, so what is an event? An event is a subset of this. So an example would be something like, this thing could be equal to something like, so first of all, it's a set. And then in it should contain feature label pairs. So if we just talk of the simple case where we have like one feature, number of rooms, and price, it might be something like 2 rooms, and let's say like 200,000. That's what it is. And then it can contain another feature label thing, which is like 3 rooms and 400,000. And maybe just these two. So this is like this event. And this would ask, what is the probability that the first thing I sample, like the first house price pair I sample, is either this or this? It's not, we're not gonna usually write it in like this very explicit way and stuff, but like this is like formally what it would look like. It's like this just means some subset of the possible like feature label pairs. This is one possible subset. It contains 2 of these. There's a lot of them, and these would be much bigger usually. So yeah, you can have 2 event sets. So this is the event set talking about this random variable. This is the one talking about this one. You can just as equally imagine you can have one event which talks about all of them jointly. That would be like an event. So you could have like an E, which is a subset of what? A subset of the whole data set's outcome space, which is Zn, right? And this would mean, okay, so like once again, going back to the coin example, I think is helpful, is that this here you could think of as n coin flips, and this event would be something like, so first of all, it's a set of outcomes, right? So I could ask like, I can give the event some values in that set, and maybe I can give it 2 outcomes, which is that all the n flips are heads, or all the n flips are tails. And then there's all these other combinations and stuff. But that's what this event would look like. It would be like, actually listing what every single one of the n coin flips are, or listing what every one of the n feature label pairs are, while these events here are talking about just the individual things. So this would mean, like if I were to, for the coin flip thing, I could just write like, for instance, this is the event where you just, let's say just get heads. That's just asking what's the probability of this first coin flip being heads? And then you can, there's not that many events for the coin flip thing. There's either that or tails or heads or tails, but so I think it's always good to kind of like remember maybe this coin flip thing and then map it to this more complex story here of what independence means with coins, what n coin flips means, what are the events of a single coin versus the events over all the coin flips as one space. Okay, and I'm going to answer one question here, which is asking, could you explain the line just before the equivalently subsection? The third assumption again. Oh, yeah. So I suppose it's like this. So yes. So once again, what this is saying is really saying what do these two assumptions mean? And yeah, I can repeat this again, which is that the thing we start with is a distribution over the whole data set. The whole data set is objects of this type, right? So if a probability distribution is over the whole data set, I can put in objects of that type. So that would mean like the first random variable equaling something and so on. I could have equivalently wrote something like, and I'll finish here. I could have wrote something like the z itself, which represents, or sorry, not z, d, and I could have wrote it as it's an element of this bigger event space E. And then let's see how much time. Okay, I have like one or two more minutes. So the second thing here, this is just the independence part. So maybe I can write this is like using assumption 1, and then this one is using assumption 2. Independence allows us to multiply. So these are all multiplied. Independence allows us to multiply. And identically distributed means that all of these distributions are the same. Yeah. And yeah, maybe I'll answer one final simple question, which is what's the difference between a marginal distribution and a probability distribution? So a probability distribution is this like thing that takes in events. And there's different kinds of probability distributions. There's a joint probability distribution, which is over the whole multivariate thing. There's a marginal one, which is just over one random variable from that joint thing. There's a conditional distribution. All of these, like conditional, marginal, joint probability distributions are just, they're all probability distributions, but they have like a certain type. But they all take in events, but different kind of events from a different outcome space. But so they're all probability distributions, but they're different probability distributions. Yeah. Okay, I will end it there. Thank you.